yesterday we finished discussing the transverse field Ising model in a driven magnetic field, and I also gave you all the steps necessary to calculate this elusive quantity entanglement entropy for L consecutive spins. That can be reasonably easily calculated in that particular model due to the solvability of the model, right? There are some steps, and I indicated those steps, and hopefully you can do the calculations yourself after that. Okay, so that was one thing. Then we also saw that if we take some particular model of fermions and drive it periodically in trine, you can get what is known as the anomalous Fluke-Anderson insulator. That state of matter had the very unusual property that while states in the bulk were all localized, there were chiral edge modes. Okay? And this cannot happen for a normal Anderson insulator which is undriven, because if all states are localized in the bulk, there cannot be chiral modes in the boundary for an Anderson insulator. Okay, so that was pretty interesting. Okay. So there are some works by the subset of authors whose reference I gave you while discussing the anomalous Anderson insulator on how it can even generalize to interacting systems, right? Because the natural question is what happens in interacting systems. But then it crucially uses something which we haven't discussed so far, and I hope to briefly discuss today, which is many-body localization. Okay? So that is a crucial ingredient in trying to stabilize that anomalous Fluke-Anderson insulator into an interacting regime. Because see, the problem in an interacting regime is, as we discussed, right, from Fluke ETH, things should heat up to some trivial state where the correlation functions only depend on the structure of the Hilbert space. So it's like an infinite temperature state, even though it's more appropriate to call it a steady state, a featureless steady state. Okay? So, so we need to somehow get out of that problem. So one way of getting out of that problem is to try to take a state which is many-body localized and then drive it. But to my understanding in this school, many-body localization has not been discussed. So I'll introduce it briefly. It's anyway a rather subtle topic, and maybe some of you are aware there are new controversies emerging all the time. But anyway, I'll just tell you what you need to know at a particular stage, after which you can start following papers on your own. And then I hope to discuss, after discussing many-body localization, a very interesting Fluke phase of matter, which is known as a time crystal. Okay, so that's the plan. Okay, and I have a lecture in the morning and in the afternoon as well. So hopefully, if I finish time crystals by the afternoon, I'll even tell you how to stabilize a time crystal in a pre-thermal sense without even invoking many-body localization. But we'll see how far we go. So that's the plan. Okay, so let's go ahead, and again, if you have any questions, you can stop me at any time. Okay. So actually, Shubhrat already introduced very secretly a minimal model for many-body localization. After I go through some steps, you will see that model reappear. There was some model with just some tau yz's interacting with some exponential decay that he introduced, right? So you will again see that model emerging here. So, as I said, this is going to be an extremely quick review of only the very main points that we require. It's not an in-depth review of this subject, which essentially needs a lecture series of its own, okay? But, yeah. But I can point you to a very excellent review, and that is the following. reviews of modern physics, and here's the review. Okay. So what is the main point here? The main point here is that, and okay, right now I'm not introducing any Fluke structure here. You can just think of undriven problems again. So the main point here is, as we learned, in a generic system, which has many degrees of freedom and is isolated from anything else, so it just has its own Hamiltonian, which is an interacting Hamiltonian. If you look at a subsystem which is finite, okay, the rest of the system acts as an effective bath for this subsystem. That's the foundation of all this thermalization and ETH, right? So this is a very important ingredient. What is going to happen is, there are certain classes of systems called many-body localized systems, and these are like many particle or interacting versions of Anderson localized systems, where due to strong disorder, this picture stops working. So somehow in those systems, due to strong disorder, the rest of the system cannot act as an effective heat bath for any small subsystem. Okay? So really the most crucial ingredient there is that so I'll use a shorthand for this. I'll use MBL rather than writing this long thing again and again. So in a MBL phase, the most important thing which distinguishes it from this kind of a phase is that excitations get localized. So what is the meaning of this statement? So in a generic theory which satisfies ETH, suppose you start with a eigenstate of such a theory. And of course, you know the theory lives in real space. So this is a real space lattice. You go ahead and prepare it in a quantum state, which is an eigenstate of the system. Okay? Now on top of this eigenstate, you do some local operation. You hit it with some local operator of your choice. Okay? So of course it disturbs the eigenstate. Right?
What is that mesh supposed to represent?
That mesh, that it's a lattice theory. Yeah. And this is like space. And because I'm hitting the eigenstate with the operator localized somewhere, that disturbs the eigenstate locally at time t equal to 0. Okay, that's the meaning of this picture. Now, if the theory is ETH satisfying, then what happens is if you wait long enough in time, this excitation will spread. This excitation will spread and it'll just become this. It'll just spread out completely after a certain reasonable amount of time. Okay? That means that this excitation is not localized. You understand? However, in a many-body system, in an MBL phase, this is not supposed to happen. What will happen is, if you put this excitation like this, it'll of course grow a bit, but then it won't stretch out all the way and spread in the entire system. That's the crucial difference. Okay? What might happen is that this excitation will, that this excitation maybe will look like this at late times. Okay? And in fact, this spread of the excitation can be characterized by some length scale, which I call xi localization. Okay, I'm being a bit schematic here, but it's good to just get the physical picture in mind. Okay, so basically there might be tails here, but the important thing is that there is a length scale associated, and I call it this. So this excitation has not spread out; it's still localized. Of course, it changes a bit due to the dynamics of the Hamiltonian. So you hit some local operator on your eigenstate, that gives you some different state, right? So let's call it psi 0, right? Then what I'm doing is, I'm just propagating psi 0 in time by the Hamiltonian of the system. That's what I'm doing, right? And I'm seeing what happens. So if it's a thermal theory, if it's a theory which satisfies ETH, this happens. If it's a theory which is in the MBL phase, this happens. That's a very crucial difference. Okay? So because of this property, if you start with an initial state in an MBL phase and you let it go, right? By letting it go, I mean this, then the memory of the initial state is retained. So just to give you a cartoon of that, and this is in fact how MBL phases were also sort of discovered in cold atom experiments. Suppose you have a spin system in mind again, a 1D spin system, one-dimensional spin system, and maybe you prepare the initial state like this. Maybe there's an upspin here, a downspin here, an upspin here, a downspin here, and so on. Okay? Suppose you prepare the initial state like this. So if you, of course, look at the magnetization looks like this. So 1 here, 0 here, or rather -1. But let me just draw 1 and zeros. You can think of it as densities as well. Right? So this is 1 and this is 0. Now suppose you propagate this in time. Suppose you propagate this in time. If you have a theory which thermalizes, okay, how do you think that this function will look at late time? How do you think this function will look at late time? So you understand the question, right? So I have drawn you something, some state, initial state, where these guys are ones, these guys are zeros, 1, 0, 1, 0. And I've just let it go. I'm asking if this theory thermalizes, how would this kind of a profile look at late time? Yeah, but what is that number? Yes, exactly. So it couldn't have been anything else. So it'll just look like this. However, if it's a many-body localized system, of course there'll be some dynamics and these guys will change, but it might look like this.
This could be half, like it could thermalize if there are boundaries, right?
Sorry?
If it's an infinite system, it would never thermalize.
That's correct. That's absolutely correct. If it's an infinite system, it will truly never thermalize. But let's say you're just looking locally, then you will still see that it thermalizes. So okay, this is a local property. For this local property, it will thermalize. Yeah. So it'll look like this for a many-body localized system. So you see there is a memory left of what was high and what was low. Right? That's very important. And this is happening because of that property. Okay? Good. So there is another thing here. You see, when people talk, why did I introduce this picture? There's a very important reason I introduced it. When people talk about something being many-body localized, you should ask the natural question of what is the localization length? Because for anything which is localized, there's a natural localization length. See, for an Anderson insulator, it's very easy to imagine what the localization length is, right? Suppose there is a problem of electrons in one dimensional, and you just introduce some chemical potential, which is random in space, right? That leads to Anderson localization. Now the point is, if you just look at the one-body wave functions, because after all it's a non-interacting problem, if you didn't have these chemical potentials, then the wave functions look like plane waves in real space, right? All of you agree. But suppose you have this and let's say you make this sufficiently large. In fact, that's not necessary in one dimension, but suppose you do that, then the wave functions sort of look like this. Okay, there's some length scale associated. And you can just look at the wave function and figure out that length scale in the Anderson localization problem. But in a many-body problem, this is completely different, right? You have Fock states or eigenstates. There is a spin everywhere in some complicated superposition state. What is the meaning of localization here? I cannot stare at my many-body wave function and tell you a localization length. It's impossible because there is a spin everywhere on all sides, right? So I hope you understand why it's not obvious how you define localization length. Instead, how you define localization length is in this setting is precisely this recipe. Okay, at least as a thought experiment, you can do that. You take an eigenstate, you hit it with a local operator that perturbs the eigenstate locally, then you see how that perturbation evolves in real space, and at late time, from this you get a localization length.
Is this unique then?
Unique.
It happens then for different operators?
Yeah, of course. This is a localization length can never be unique because it's some finite number, so it depends on your definition. Yeah. But that's true here also, right? Suppose you have a function and you have been asked to calculate at what length scale it localizes. Somebody might say, oh, I'll draw a line here at 1/10 of the maximum of this function. You'll get one number. Somebody else might say, oh, no, I'll draw it at 1/100th of the maximum of that function. You'll get a different number because it's a finite number, so there are different recipes. But there's a sensible definition of a localization length.
And it could very well be possible that there are some local operators for which this MBL phase doesn't emerge, and there are others for which they emerge, or generically.
No, okay. The point is there would be no operator which will entirely diffuse. Yeah, if it's an MBL phase. Yeah.
The length depends on the choice of the.
Of course, yeah, but yeah. Good. So I hope you get the sense of how you can define the localization length here. Okay, good. So now, as I said, this MBL phase, lots of things are not completely understood still, and there are various issues. But for us, I'll just give you the things which are at least understood at a reasonable level numerically, right? And there are crucial differences to thermal phases. If you look at the same kind of lattice sizes in numerics again, right? There are big differences, right? So, yeah.
So, of course, I mean, I'm outside the field, so I don't know much, but whatever I could, gather, so I've always seen MBL being detected by looking at, level statistics and this sort of thing.
Yes.
This sort of dynamical picture I haven't seen. So, from what I missed out, or are there really...
this dynamical picture?
No, this the one that you...
Oh, no. For example, in cold atom experiments, this is literally how they argue that they might be seeing an MBL. Because, of course,
in some numerics...
in some numerics also, they must have also done it.
they must have, but have they?
No. Well, again, I'm also a bit of an outsider to this field, but I'm almost sure that they have done it. Yeah, because I think they have done it. This is called imbalance. I think there are several papers. So this is imbalance for a very simple reason that this is something here and this is something here, right? So basically, people see whether the imbalance relaxes to 0 or not. And I think there are several numerical papers where they have seen the evolution of imbalance. Yeah, that's the crucial term to search for. Somebody had some comment or question?
No, actually, I was a bit confused about that diagram. Now it's clear that it was on time.
In time, yes. Yeah.
But the figure was also on time.
Okay, anyway, so let's go on. So what is a prototypical example of this kind of a funny phase, right? And of course, sorry, one more comment. You can clearly see, because the excitations are localized, you can clearly see why that patch, why the rest of the system cannot act as an effective heat bath for that patch, right? Because to act as an effective heat bath, you need to transfer excitations all the time. But if excitations are localized, it's impossible that the rest of the system can act as an effective heat bath. Okay, good. But let me also just make a small comment about what Shamik said about level statistics, and I'll come to it more. I'll discuss it a bit more. So the point is, in MBL, there's also another very interesting thing. There is a notion of an emergent integrability. So this word emergent is very important here. We'll see what that means. Somehow there is integrability here, but unlike usual integrabilities which are fine-tuned. So what that means is, suppose you take the transverse field-Ising model and add a longitudinal field to it. As soon as the longitudinal field becomes any non-zero number, the integrability is lost. So it's fine-tuned, right? It's only at a special value of the couplings. Unlike that, here, MBL emerges as a phase So there are a family of points in parameter space which are all integrable. Okay, so there is a very interesting way in which that happens, but they are all integrable. Okay, so let's consider some prototypical example. So you can take any of your favorite model in one dimension, some spin models that we have been discussing, and you can disorder it by some random field or something. And if the field is random enough, generically the expectation is this kind of a thing can happen. Yeah.
Will you be talking more about this?
Louder?
Will you be talking more about this emergent?
Yeah, I will, but not too much, because again, as I said, I want to just give a very...
This integrability emerges.
We'll come to that. So let's consider a prototypical model. So let's take our usual XXZ chain, spin half again. So this is some nearest neighbor coupling. Let's put some term like that. Now comes another term which disorders the problem. This term. Okay? And I pick these fields, let's say from some random number distribution independently at each side, and let's say it's some box distribution, right? With a width 2w. Okay? So of course, if this w is extremely small, then there is weak disorder, right? You understand that. If this w is 0, there's no disorder, right? Because then this HIZ is always 0. And if this w is large, then the disorder increases. Okay? So you can in fact use the same Jordan-Wigner transformations we did to also sort of fermionize this problem. So by the way, if you just look at this problem, this also has an interesting integrable structure, but it is something slightly different from what we saw in the transverse field Ising model. This is what is called as a Bethe integrable problem. Okay? But of course, if you add this kind of a term, that integrability is lost, that Bethe integrability is lost. Okay, so if you use Jordan-Wigner transformations here, just like we did last time, then this maps to a problem of fermions where there is this hopping. So this T is basically proportional to this J perp. This V is proportional to this JZ. And there are terms like this. And then this guy becomes something like this. So this is like a disordered chemical potential, right? For the fermions. And this epsilon I is again in this domain. Okay? So you can easily see here that when Jz is 0, this is like free fermions in a disordered chemical potential background. So this is like Anderson insulator, right? But of course, when this is non-zero, this is an interacting problem. This full problem is an interacting problem. Okay? Good. So what is the phase diagram of this problem? So when I say phase diagram now, I'm actually talking of all eigenstates. Okay, I'll come to this point again. So I'm talking about all eigenstates. So let's say in my numerics, I said J perpendicular equal to 1, let's say, right? There are many parameters here. So let's say I said J perpendicular equal to 1, and let's say I also keep W fixed to some number. Then the only thing to vary is this Jz, right? That thing. So now, as I said, if Jz is 0, then it's nothing but the Anderson insulator. However, as you turn on Jz, it becomes a interacting theory. And in fact, this entire thing is an MBL phase. and then there is a phase transition, and then it becomes a thermal or an ETH satisfying phase. Okay, and this is increasing Jz. Jz increases in this direction. So Jz equal to 0 is of course very easy to understand. It's the Anderson insulator, but the rest of it is a many-body system.
Is it 0 temperature?
Yeah. This is all at 0 temperature. So, okay, let me clarify what I mean. Let me just draw another phase diagram and let me clarify what this phase diagram means. So this is at, okay, yeah, this is at 0 temperature, but actually I shouldn't even use the word temperature here. I'm looking at the properties of the entire spectrum together. Okay, so, yeah, so this is one phase diagram where these two are fixed and I'm just varying Jz. The other phase diagram is that maybe I can keep Jz to be fixed. J perp is still 1 and Jz is some fixed number. Okay, and then of course the only thing to vary is W. But I already told you that if you just have W equal to 0 so that you can ignore this term, that problem is Bethe integrable, that top problem. Even though in this picture it looks like interacting fermions, but you can do some further transformations to show that it's somehow integrable. Okay, but we won't discuss that. So this point is integrable. So you're just changing this W here. So this is integrable. Okay. And then this region is thermal. But when this W becomes strong enough, so that when the disorder becomes strong enough, then again an MBL emerges. So in fact, the first set of numerics, or one of the first set of numerics which people did on finite systems to figure it out, they actually kept the couplings like this, and they figured out that this W critical from finite size studies is roughly 3.5 in a 1D chain. Okay? So how did they do that? That will also partly answer some of the questions raised. So how did they figure out? How did they distinguish between a thermal phase and an MBL phase? So if you remember, we discussed about this level statistics previously, right? So you basically order the energies from decreasing to increasing after resolving all the symmetries, right? And then you look at the gaps and took the ratio of consecutive gaps, and from that you can draw a histogram, right? And we argued that if you look at that level statistics, which can only go from 0 to 1, we argued that, if a theory is ETH satisfying, the graph looks something like this, whereas if it's somehow integrable, then the graph looks something like this, right? So if you look at the level statistics here, in this region, so you look at the entire spectrum, and level statistics is a property of the spectrum which tells you whether there is level repulsion or not. If you look at the level statistics here, then it'll look like this. Whereas if you look at it here, it'll look like a Poissonian. So there would be no level statistics. That's very important and crucial. So in fact, more particularly in these first studies, what they looked at is expectation of R. And we discussed that this expectation of R is basically 0.53 if ETH is satisfied, and it's something like 0.39 if there is some kind of an integrability. Okay? So what these guys saw was the following. And so let me mark two numbers here. So they did this exact diagonalization studies on various chain lengths, maybe 8, 10, 12, 14, 16, right? On the initial studies, of course, now you can go bigger. But anyway, whatever you do, you'll get something like this. sorry, let me draw it correctly. So this system size is L1 and this is L2, and L1 is bigger than L2. So, you know, this is a nice kind of a finite size scaling plot. That's why I'm showing it to you. I mean, you must be used to seeing these kinds of things when you do Monte Carlo or something, and you do things like Binder cumulants and all, right? Maybe some of you know how to do that, right? So basically the point is this. So let's look at the thing carefully. Of course, I don't have access to infinite sizes, right? But if you did have access to infinite sizes, then this average R should have gone to 0.53 in the thermal phase and should have gone to 0.39 in this MBL phase, because I said that in this MBL phase there's some emergent integrability. In fact, in the numerics also people see that. And at the phase transition, it might be some other non-trivial number in between. It might be, right? So you see, this is exactly what they saw in the initial numerics. In fact, I forgot to give the reference of that paper, but it was by Arijit Pal and David Hughes. Yes. Okay. Okay. So let's say you are at some particular length. So you see a curve like this. Now you increase the length of your chain. You see a curve like this. So what is happening here? So reasonably away from this transition, which is roughly this crossing point, reasonably away from this transition, you can clearly see, at least as a function of system size, this expectation R is approaching this 0.53. Similarly here, as a function of system size, it's approaching 0.39, right? And then in the neighborhood of the transition, and that's how they estimate the transition, there is this W star, which is 3.5. Okay, and of course, if you look at some other length which is even bigger, then ideally this curve should look like that, right? Okay. So in the thermal phase, if you look at the level statistics from all the eigenstates of your theory, then it looks Wigner-Dyson. Whereas in the MBL phase, it looks like a Poisson. Secondly, if you look at the, let's say, half-chain entanglement entropy, something which Subrata also mentioned. So suppose you have this 1D chain, and you know all the eigenfunctions here from your numerics. You cut the chain in half. Of course, there's a fictitious cut, and you just integrate out these degrees of freedom, and you find the entanglement entropy from the reduced density matrix. Okay. Then, typically for a thermal theory, it satisfies what is known as a volume law. Okay. And the entanglement entropy is reasonably high. In fact, if you double the system size, the entanglement entropy doubles. Okay, so people did see volume law scaling for entanglement entropy here. Okay, but here, so let me make a divider. Here they saw area law scaling instead. So what that means is, for most typical high energy states, if you double the system, the entanglement entropy does not seem to increase, right? Which is very atypical of thermal systems, but this seemed to happen here in this side. Okay. The other remarkable thing which is related to dynamics is, if you look at if you start from a product state, some random product state, right? And you just let it evolve and monitor the entanglement entropy again. If you remember from Subrata's discussion specially, and also from the kinds of plots we saw for the transverse field Ising model, typically the entanglement entropy grows linearly as a function of time for a fixed subsystem, and then it saturates to some value. Okay? Yes?
W0, will it again go back to 0.39?
Where? Here? Yeah, that's correct. That's correct. That's absolutely correct because it's an integrable theory, right? They of course did not stretch it so much, but that's a fine-tuned thing in the sense that if you have a really big system, it's only 0.39 here, but then it'll jump to 0.53 here. It's really fine-tuned. This integrability is fine-tuned. But here, it's supposed to stay 0.39 if it's truly an MBL phase all the way through. Okay. So where was I? So here, if you start with some random initial state and you just let it evolve and monitor the entanglement entropy, here the entanglement entropy grows linearly in time before saturating. But here, the entanglement entropy grows logarithmically in time. And basically the minimal model to explain that was already shown to you by Subroto. Remember that he gave you an explanation of a sort of a funny looking model which had a log t, right? It wasn't a generic model as he repeatedly said. For a generic model you'll get this, but here you get this, right? So you see there are important differences here, right, in the spectrum, right? Here there is Wigner-Dyson volume law scaling for entanglement entropy of high energy states. If you start with the random initial state, then the entropy seems to increase linearly in time, right? So that's known as this ballistic propagation of entanglement. This is a generic thing. But here, in this entire region from W star all the way to W tending to infinity, you see Poisson statistics, you see area law scaling of entanglement entropy for high energy states. And if you again start with the random product state, instead of this kind of an increase in time, you see a much slower increase in time. A log t is much slower than t, right? So, okay, good. So let me quickly, you remember I gave you a hand wavy argument of excitations being localized, and from that you can define a localization length scale. Let me give you a quick similar hand wavy argument for why there is area law scaling here. Okay, so let me just do that right now. Oh. So imagine for this kind of a system, I am at some W, some value of disorder, which is sufficiently high such that I somehow have an inkling that the phase is an MBL phase, right? So there is this spin chain or whatever. It has some short range couplings, and I'm calculating the half chain entanglement entropy. Let's say I switch off this coupling. Anyway, you can see that there are only couplings which connect two bodies and there are one body coupling. So let's say I switch off this coupling. Then this chain becomes disconnected to this chain. Whatever complicated thing happens here and whatever complicated thing happens here, I know that the half chain entanglement entropy in this case has to be 0. All of you appreciate that, right? Because, yeah, okay, anyway. But this phase is in an MBL phase and this phase is also in an MBL phase, right? But I've just switched off this coupling. Okay, so it's like there's a H which has HA, let's call this A and let's call this B, plus HB plus HAB, and I have just switched this off. Okay, so then whatever the wave function is, I can decompose it like this. This wave function might be a very complicated wave function. And this wave function might also be a very complicated wave function. But because of this property, I know that the total wave function has to look like this. So the entanglement entropy of this particular thing has to be identically 0, right? I know that. Now, let's say I switch this coupling on. Let's say I switch this coupling on. Switching this coupling on can also be thought of as introducing a local perturbation in your system, because after all, this is local. And that creates an excitation, but that excitation can only be localized, right, from what we have discussed. So it will sort of create something like this at some length scale like this. So whatever happens, things will only get entangled till this length scale, if you believe this picture. Therefore, this thing will basically be related to this localization length scale. it'll be a finite number and it'll be related to this localization length scale. Okay, that's why you should get an area law here, because there's some finite number here, right? So again, the argument here is the following. It's a deceptively simple argument. The argument is, I go to a situation where I know that the entanglement entropy is 0, then I turn on this particular coupling, which I had switched off. But this particular coupling turning on is like hitting the thing with a local operator, because after all, it is a local operator. But that can only affect the system if I believe in that picture which I introduced till a certain length scale. It cannot affect the system very far away, right? And I'm taking the entanglement cut here, right? So because it only affects things till this length scale, the entanglement entropy can only go from 0 to a non-zero number, which is some function of this guy, but some finite number, right? That's the point, okay?
You say like volume and area, I mean, it should be synonymous with bulk and boundary. I mean, that could be a better way of, like, when it is volume, it's basically bulk effect, and then...
Exactly, so this is a boundary effect. In some sense, this is a boundary effect. Yeah, because, yeah, you can say it like that, okay? But the important thing is that the excitation does not spread, yeah. Okay, so that's why you get area law here. But of course, in a thermal phase, this picture would break down, because this excitation would spread and then the entanglement would be much more complicated and much more diffused, and then you get a volume law due to that. Okay, good. Now, let me very briefly discuss this emergent integrability aspect of this problem. Oh, so maybe I'll bring down that XXZ model and I'll write on that part of the board. Where is that model? Yeah, so this is the model, right? This is the model. So, in that HXXZ model, let me put J perpendicular, this coupling equal to 0. So first, consider J perpendicular equal to 0 for that XXZ. Okay, can someone then tell me a class of simple operators which then commute with this Hamiltonian? So I've just put J perpendicular equal to 0. Sigma z at all sides. All of them individually commute with the Hamiltonian, and of course they commute with each other, right? So, in this thing, we know, and right, all of them commute with each other and also with the Hamiltonian. So these are local conservation laws. Right? So of course, this theory is very simple. It's not a full-blown interacting theory. But when you turn on small j perpendicular, if you remember the phase diagram, if you turn on a small j perpendicular, it's still supposed to be in an MBL phase, right? Here, it's this, right? But if I turn on a small j perpendicular, it's still supposed to be in an MBL phase. So put. But then, of course, it's a much more complicated problem. It's a much more complicated problem, and usually you would not know how to solve it. But then what is this emergent integrability? So the claim is, even in this limit, there are some dressed operators which look like this and which have a property like this. So these are dressed operators. So how do these operators look like? These operators in the literature are sometimes called L bits. Of course, finding these operators numerically is a very difficult task. There are some nice papers, for example, by Frank Polman and many others, where you can see this. This is a very involved task. Even in his papers, he was not able to find all the L bits and stuff like that. But anyway, but as a picture, this is a very interesting and a nice picture. So what is the picture? So the picture is that when you turn on these interactions, somehow there are still n conservation laws here, and these conservation laws still have a sense of locality. That's very important. Okay, so when I write this equation, you'll automatically see where the sense of locality emerges. So this thing plus that thing, which I'm writing downstairs. Plus higher spin terms, plus higher spin terms. First step where locality emerges is that this z is not equal to 0. Second step where locality emerges is that these functions, which are some complicated functions, nonetheless decay like this, where, one second, where r is measured from I. Yeah?
Say the candidate is a number.
Yeah, it's a number. It's a number. Here it can only be a number, right? So yeah, it's a number. So this is a number. This number is non-zero, right? And secondly, there are many kinds of terms here, but they're all decaying with a certain length scale, and that length scale is again related to that localization length scale which I mentioned to you earlier. And here the distance is always measured from this point I. So maybe I can just say Rij, right? Just to remind you of that. So you can immediately see where the sense of locality is emerging from the site I, right? So of course, these are much more complicated objects. They are not simple objects like this, but the claim is that in the MBL phase, there should again be n such objects which are mutually commuting and as well as commuting with the Hamiltonian. That's the claim. Okay, this is in fact what is called as the L-bit phenomenology.
And when I put J perpendicular equal to 0 in these definitions, I should get back.
Of course, you should get back, if you literally could have calculated this, you should get back that all these guys go to 0 smoothly and this guy goes to 1. Yes. But as I said, that's a difficult task. So this is a very, very good phenomenological picture. Okay. If you really want to get it microscopically, that's a hard thing to do. Okay. So there is another way to understand this thing, which is the following. Okay, but let me just write one more step and I'll tell you a way to understand this thing later on. But anyway, the step is the following. So if you somehow then write the Hamiltonian in terms of these tau z variables, then in the MBL phase, the Hamiltonian generically has to look like this. And here you will see the Hamiltonian that Subrata was mentioning and discussing a lot. Again, these terms decay with a localization length like that. These terms also decay with a localization length like that. Plus dot dot. And you have already seen this Hamiltonian, right? And for this Hamiltonian, he proved that the entanglement entropy, if you start with a generic state, goes like that. So you see, Shamik, why this is a nice phenomenological picture. It explains some very unusual things in a simple way. But it doesn't mean that the picture, I mean, it doesn't mean that you can flesh out all details of the picture in a systematic numerical calculation very easily, okay? It's a very nice picture. Good. But now let me tell you another way of thinking about this. So suppose I give you a complicated Hamiltonian on, and you like go and try to diagonalize it, writing some routine or something. Essentially what you're doing is finding the appropriate unitary matrix, which when you apply on the Hamiltonian, or rather when you do a basis transformation, it diagonalizes your Hamiltonian. That's what you're doing mathematically, right? So basically, given any Hamiltonian, no matter how complicated, essentially what you're trying to do is find a suitable unitary matrix which diagonalizes this Hamiltonian, right? All of you agree with that? So then you would say, oh, if that is so, then I should be able to take in any problem, no matter how large or small J perp is, I should be able to take those tau I z's and just get tau I z's like this. Well, in a mathematical sense, you're true, but it doesn't take you very far. Why? Because see, if you want to go from here, where the states have essentially zero entanglement, which you can also think of as area law entanglement, to a thermal regime where the states have volume law entanglement, then this unitary matrix has to be extremely non-local in real space. So what I mean by that is the following. See, the U can always be written like this. So you can ask whether S is local or non-local in real space, right? So if you want to go from a problem which has sort of unentangled states to another problem which has volume law entanglement, then this S has to be necessarily non-local in real space. So it's like you're mixing a lot of things, right? So then when you do this operation here, then there would be no sense of locality here. There would be no sense of locality in that definition. Okay, I mean, these tau I z's would be some extremely complicated functions, and you won't be able to figure out the initial site where this sigma I z started from. I mean, firstly, z would be 0, and then there would be no simple length scale here which will be dictating these things. So it will be an extremely complicated mess. However, if you want to go from unentangled states to area law states, then you can get away with a local S here. Okay, that's the important thing. So it's just coupling a few states at a time. Okay, and then it's conceivable that this operator still has a memory of this initial site. It's conceivable, right? Because it's somehow local in real space, and that's exactly what's happening here. So that's the intuition. Okay? Good. So another thing to point out here is the following. There is another very important way in which somehow these unentangled states just become area law states and don't immediately become volume law states. So see, when you turn on interactions in any theory, let's say you're writing an extra term to some non-interacting theory, and let's say that extra term is some lambda times O, which is introducing interactions. So usually what you care about is like when you do perturbation theory, you care about things like these, right? Okay. So now the point is, in an MBL phase, see, why doesn't usual perturbation theory work? The usual perturbation theory doesn't work in this regime. It's because the level spacing is extremely small. So no matter how small your perturbation is, the level spacing is so small that perturbation theory immediately breaks out. However, in an MBL phase, what happens is the off-diagonal ETH, which we also discussed briefly, spectacularly fails. So what really happens is, for an MBL, most of these off-diagonal matrix elements are 0. Most of them are 0. Okay, so then it doesn't matter how small your denominator is. Only some of these matrix elements are non-zero. But the matrix elements which are non-zero, which are connecting two states, these two states are reasonably far in energy. So you can still conceive of doing a proper, well-defined perturbation theory. Okay, so let me. Yeah, so there is an extremely complicated semi-proof of this by Imbri, but again, just take it as a picture. But there are some rather complicated proofs, but they are not, I mean, it's quite conceivable that those proofs have some loopholes somewhere. They're rather difficult proofs. Yeah. But, I mean, at least for the sizes where you see this Poisson statistics and all, this picture is right. I don't know what happens in the extreme thermodynamic limit, but in the sizes where you see this picture has to be right. The picture is that if you take an MBL eigenstate and you hit it with some local operator, then, so you take an MBL eigenstate and you hit it with the local operator, and then you see its overlap with the other eigenstates of that MBL phase, most of the times you will get 0. So it will only couple you to few other MBL eigenstates. It will only couple you to few other MBL eigenstates. Okay, that's in fact related to the fact that the excitation doesn't travel too far in space. Okay, because in a thermal theory, if you do that, it will couple you to an enormous number of eigenstates. That's why the excitations just relax. So you see, for any system size where those things are observed, this thing should happen. Now your question is whether this holds in the thermodynamic limit. My answer is I don't know. I don't think anybody in the community knows for certain. There are some reasonably interesting proofs in the literature, but it's possible that those proofs might have loopholes, which might emerge in some extremely long sizes, right? So I'm just being careful because it's not settled, this issue. Okay, good. So this is the phenomenology of MBL. So I'll take a pause here and see if any of you guys have any question, because after that I'll start discussing Fluke MBLs. Yeah, go ahead.
So in the MBL case, these L-bit operators can be at most a function of S number of, say, xi number of sigma is operators where xi is the local agent. Is that correct? Because
yeah, because of course these other things are decaying even faster. So I can in principle truncate this somewhere. Yeah. But again, as I want to say to you, this L-bit picture is an excellent phenomenological picture. But if you literally want to find the L-bits, I think there are great difficulties. Suppose you ask, can I find all the L-bits numerically? I think it's a very difficult task to do. Yeah, there is some progress deep in the MBL phase, but as we start going towards the phase transition, it becomes extremely complicated, even in most advanced numerical calculations. But yeah, anyway. Any other question? Yeah?
That picture, if you increase the J perpendicular, at a certain point the C localization
will go to infinity, and that's the thermal thing. That's the thermal transition. Right. Of course, whether xi localization goes to infinity continuously or it jumps to infinity so that the MBL transition is continuous or first order, those are delicate questions. But you are correct in the signature of the thermal phases that xi localization should go to infinity. Yeah, that's where you would not have any memory looking at tau Iz as to where the original sigma Iz was, because your unitary operator would mix everything. Yeah. Sorry, what? No. Oh, so, okay. I don't know whether there is any very simple way to tell you that. It's, sorry, I don't know how to say it in words in a very simple way. Yeah. No, it's more complicated than that. There are some arguments which are used here. about certain terms being small and small to a certain degree in a perturbation theory is delicate. If they are not that small, then certain arguments in that perturbation theory can break down. So sometimes people say it like many body resonances and all, but those are just words, right? Ultimately, yeah, I don't know how to tell you in a very simple manner how it might break down. But what I'm trying to tell you is, for system sizes where you do see those signatures of MBL, remember I wrote many signatures of MBL, Poisson statistics, S of t increasing as log of t, and area law scaling of entanglement. In that regime, for those length scales, this is a very good picture to keep in mind. Now, if you ask me whether this picture survives in the thermodynamic limit, my answer is I don't know. Okay? It may. Some people strongly believe that in one dimension at least it may.
Also, all the other signatures,
Which one?
like statistics and
Oh, but that's what I said, Poisson, right?
those which are still relatively system size.
No, but you can only increase system size till a point in your calculations, right? Nobody has done the Lewis statistics for 40,000 spins, right? So how do you know what is going to happen there, right? So what I'm just trying to tell you is that there are some proofs here. Those proofs are not ironclad. I mean, there are many situations in physics where that is the case, right? And we don't have a extremely good argument to say with absolute certainty that those loopholes might not be important in the thermodynamic limit. That's all. Potential loopholes. That's all I'm saying. So it's just good to be careful, right? So, okay, so let's go to Fluke MBL if there are no questions. So basically, the point that we'll see here is that suppose we are in a phase which has many body localization, then in that phase, if I turn on some periodic, if I turn on a parameter, if I make a parameter time dependence and drive it periodically in time, then A, you can have a Fluke version of an MBL, and B, you can have two kinds of Fluke versions of an MBL, right? One is a Fluke version of an MBL, which is basically like the static MBL. But the other is what I would like to call as a time crystal, where there is no static analog of an MBL, right? Remember our discussion yesterday about these winding loops and all, right? So there are some features in periodically driven problems which have no static analog. We'll see something like that right now in the rest of the lecture. Okay, good. So that's the aim. So you can look at this nice paper, for example. There are others as well for what I'm going to discuss. Okay. So in this problem, they have the following Fluke unitary. In this problem, there is this unitary. So what is H naught? okay, where this HI's are taken again from a box distribution. This H1 is this term. Okay. So in the numerics, they again try to, okay, I'll come to that. In the numerics, they fix the following couplings. Okay, and then the only tuning parameter is T1. Okay, the only tuning parameter is T1. So let's just stare at this for a while and see what is going to happen. Okay, so this is the unitary of the full cycle. There are two terms here. So the term H1 turns on for a time T1. So what is this H1? H1 is this theory, and this has no disorder. And basically, the excitations of this theory would look like plane waves, right? I mean, in some reasonable sense. Okay. Then, after time T1 is over, for the next time interval T0, you turn on H0, right? And H0 is this theory, right? And this has this randomness and everything, right? And here, of course, the wave functions are straightforwardly localized in the sigma iz basis, right? So that's the picture. So now, let's say I fix T0 equal to 1 and W equal to 2.5, right? So basically, if this T1 is extremely small, then roughly speaking, very roughly speaking, you are giving the system a very small amount of time per cycle to even access these extended phases, right? So it's conceivable that for small T1, this thing stays an MBL, okay? Whereas, of course, if you start increasing T1, so the time scale per cycle where you are allowing the system to access these extended states, it's again conceivable that the theory might go to a thermal phase, right? Okay, so I mean, it's very plausible that for small T1, this theory will stay localized even in this Fluke problem, and for big T1, it'll become a thermal thing.
So you keep doing it.
Exactly, yeah. In a Fluke problem, you keep doing it. You keep doing it stroboscopically, right? So that's the thing. Yeah, that's the, yeah. So this is the Fluke unitary for one cycle. So yeah, so you keep doing it. But of course, if you're just looking at the problem stroboscopically in time, then of course you don't literally need to keep doing it. It's enough to find the eigenvectors and eigenvalues of this Fluke operator, right? So that's what you do numerically. That's what these guys did numerically. So yeah, I think they looked at system sizes 10, 12, 14, and maybe 16. And then they again looked at the eigenvalues on the unit circle. And then from those eigenvalues, they could figure out the level statistics, and in particular, expectation value of R. And again, now all of you are experts. Again, how would you find T1 here? So basically, they looked at expectation of R as a function of T1, and then they sort of obtained graphs like this. So something like this. So maybe this is some L1, and this is some L2, and L2 is bigger than L1, and this number is 0.39, and this number is close to 0.53, right? So they could see that there was a phase transition at some value of T1, which you can read about in their paper, okay? So the crucial ingredient here is, from this paper, it seemed at least that if you have an MBL and you drive it at very high frequencies, it seems very reasonable that it does go to a Fluke MBL. Whereas if the frequency becomes smaller and smaller, it may happen that it again then has a phase transition and goes to a problem or a phase which has fluke ETH. So that's the picture which emerges. So at least at high drive frequencies, this is stable, and then as you keep tuning your drive frequencies to lower and lower values, there is at least numerically a phase transition, and beyond it, it goes to a fluke ETH. That's the picture which emerged from their paper. Okay? So what does it mean in terms of those L-bit pictures that I had earlier introduced? At least in this region, it means that again, if you look at the fluke unitary, there must be again n operators which have a sense of locality exactly in the sense that I defined earlier, which commute with the fluke unitary and also commute with each other. Okay? But the only thing I have done is replace the Hamiltonian with the fluke unitary here. Okay? Fluke unitary is the unitary matrix for one drive cycle. Okay? And in that paper, in this paper, you can also read, you can also look at the paper for details. Again, they did those exercises, like they took a random product state and they looked at its evolution stroboscopically using this, and they could calculate the half-chain entanglement entropy and stuff like that. And again, the half-chain entanglement increased logarithmically in time. Okay? Instead of increasing linearly in time, which it would have done here. Okay? So again, that logarithmic in time comes because there is this underlying phenomenology, right? And this log t, anyway, Subhrata had discussed, as I already mentioned, right? Good. So this is the usual or simple generalization of MBL to fluke MBL, right? So this is very straightforward in the sense that all I'm doing is replacing H by UFT. So this is like a fluke MBL, which in some sense is adiabatically continued to an undriven MBL. Okay? Now I'll go to another kind of a fluke MBL, which has no analog in static MBLs. Okay, so that is the time crystal phase. Okay, and we'll see what is crucially different there. Okay, but let me just take a small pause. Any questions here? So I hope you understand the setup, right? So we have discussed this phenomenology of MBL here. It's a very brief discussion, and I was extremely careful to point out what is the open issues. But at least for the system sizes where you see those three things together, what were the three things? Poissonian statistics, area law entanglement scaling for eigenstates, and if you start from random product states, you see that the entanglement entropy grows as log of t instead of t. There, at least, it's completely conceivable that this L-bit picture is a good picture. Okay, of course, how you find L-bits and all the L-bits is a very complicated thing, and whether this picture survives for extremely large system sizes is also an open issue. But if you just focus on those system sizes where this phenomenology seems to work, and if you even introduce a fluke structure there, like this, then there is again nice evidence, again looking at level statistics and other signatures like this, that something similar happens. There is a fluke MBL, then if you keep changing your driving frequency, at a certain driving frequency, it goes to a fluke ETH. So at high driving frequencies, it stays fluke MBL. At sufficiently low driving frequencies, it becomes fluke ETH. And there's a phase transition in between.
So at low T, when
Yeah.
you expect this fluke MBL?
Fluke MBL, low T1, fluke MBL, yeah.
So you see that the entanglement entropy grows to this,
Log T.
I mean, has
Yeah, there are numerical plots in that paper.
saturation value still becomes this,
Saturation value is again some thermal value, which is also what Subhrata had discussed, right? That's also true in the undriven problem where you ultimately there's some.
I was wondering whether you get some kind of volume law.
No, you get volume law. That volume law is just smaller than what you would have expected in the thermal phase. Yeah. But the way it approaches the volume law is completely different. It's log T, not T. It's much slower. Was there any other question?
Psi 0 we will take downstream of the transversal.
Oh, the psi 0. The psi 0 you can take to be practically anything. You can take, so in fact, when they did these things in their paper, they took random product states. Just random product states. So you can practically take it to be anything. Should just be reasonably unentangled. I have unfortunately forgotten, but as far as I remember, it's order 1. As far as I remember. But you can look up the paper. Okay, good. So now we, in whatever time left, of course I won't finish it, I'll start discussing time crystals. But anyway, it'll be a nice opportunity to discuss certain things in equilibrium, especially how you should think about symmetry breaking, and that will have a generalization in time crystals. But I hope you understand why I'm making this statement here, that this Fluke MBL is basically a direct cousin of the undriven MBL, right? Because of this property. So just like the anomalous Fluke-Anderson insulator that we had briefly discussed, this phase cannot appear without the Fluke structure. Okay. So, but before discussing this, I need to discuss some other things just to clear some concepts. Okay. So, but let me just try to give you the punchline, and maybe it'll confuse you now, but you'll see that it's very important. So, in a time crystal phase, which is some non-trivial Fluke MBL, when you diagonalize U of t, you will notice something very interesting for any finite system, at least for finite systems where this phenomenology works, that all the Fluke eigenstates would be something called macroscopic cat states, or states which have something called long range correlations. Okay, so anyway, so let me expand on what this thing even means. Okay, that's the essential difference between this phase and this phase. In this phase, the states are not like that. In this phase. So let me expand on what that means. So we are actually very familiar in some sense with these things all the time. So, okay, so let's talk about equilibrium for a moment. Let's not go to non-equilibrium. So suppose a system is in equilibrium, then its density matrix looks like this, right? So the question is, suppose I have a big enough system, right? And the Hamiltonian has certain symmetries, then of course the corresponding density matrix has all those symmetries. So then the question is, how can I ever break any symmetry spontaneously, right? Because after all, if I'm given the density matrix, I can calculate any operator's expectation value using that density matrix, right? So the question is, how come symmetries get broken in equilibrium? Okay, if the density matrix preserves all the symmetries of the Hamiltonian. Okay, so what is the resolution of this paradox? So to understand this resolution, let's focus on the simplest kind of phase transitions we know at zero temperature, so quantum phase transitions. Let's say there are two phases as a function of some coupling constant, and of course, as a toy example, in your head, you can just keep the example of the transverse field Ising model, right? So there is some critical coupling GC, and for the transverse field Ising model, it's 1, below which the ground state spontaneously breaks the Z2 symmetry of the Hamiltonian, and above which the Z2 symmetry of the Hamiltonian is unbroken, right? So what is the signature of this Z2 symmetry breaking in the spectrum of the theory? What is the signature of that? If I have a really big system size and I tell you, oh, my theory has a Z2 symmetry breaking, but I don't tell you what that Z2 symmetry breaking is, how do you even know I'm correct? Okay? So the signature is the following. If you look at the spectrum here, you get a doublet, then you get an order 1 gap. Order 1 gap just means this gap does not change as a function of system size for reasonably big systems. And then you get whatever, lots of excitations on top. Very importantly, the energy gap between these two low-lying states decrease exponentially in system size. Okay? So this is the property of some discrete symmetry breaking. This is the signature of any discrete symmetry breaking in one dimension. If you break some other discrete symmetry breaking, you will get this. But maybe with more states here, if you break some Z3 or Z4, then maybe you'll get 3 or 4 states here. But this property will stay true. There'll be a doublet or whatever, an appropriate thing, where the two states are extremely close to each other. Then there'll be a gap, and then there'll be the rest of the states. And this gap won't change after a point with system size, but this gap between the ground state and the first excited state would keep shrinking exponentially fast in system size. Okay?
And how to understand that?
Understand that. Read a textbook. Sorry?
You are stating this that with increasing system size, the gap should go down.
Yeah, okay. Yeah. How to understand that? Okay. Let's see. So let's see how the states look for a finite system like this. So again, I'm drawing a cartoon of the states. The real states are slightly more complicated. Like this. So this is a cartoon of these two states, right? So, for example, in the transverse field model, if this G is very small, then suppose you start doing a perturbation theory. So if you start from really small G, then the classical ground state is this and that. Oh, sorry, this and that. These are the classical ground states. Now, and every other state has a finite excitation gap, right? Now, if you start doing perturbation theory, if you want to go from this state to this state, that happens due to this transverse field term. So it flips spins. But you have to flip L spins to go from here to here. So you need to go to a very high order in perturbation theory, and because you go to a very high order in perturbation theory, this gap is very small. That's essentially the point. Okay? Good. But the point is, if you do exact diagonalization, you get these doublets here, and these doublets don't break any Z2 symmetry. They don't break any symmetry. They respect all the symmetries of the Hamiltonian. Okay? But these states have a problem. These states have a problem. The problem is that these are long-ranged, correlated cat states. In the sense that they are macroscopic superpositions of two or more states which are macroscopically distinct from each other. See, if I look at this state, there is a macroscopic distinction between this state and this state. This state, its local magnetization is positive. This state, its local magnetization is negative. That's a macroscopic difference. And yet I'm superposing these two states. So another way of saying that these states are slightly unphysical is the following. If you calculate some correlation function in these states, for example, if you calculate this correlation function, so, okay, mz is basically related to sigma z in this notation. Suppose you calculate this correlation function. So this expectation value is with respect to either this state or that state. then this correlation function does not go to 0 as r goes to infinity. So this 2-point correlation does not decompose to these two 1-point correlations as r goes to infinity. That's why these states are called long-range correlated states. I hope you understand that. See, if there is a state where there is short-range correlation only, then these kinds of connected 2-point correlations have to go to 0 as the separation between the 2 points goes to infinity. That's the meaning of short range, okay? But in these states, this does not happen. You can actually verify this very easily. Just take this state or this state, compute this thing. You will see that this will basically be 1 as a function of r. It will just stay a constant for these two cartoon states. It won't ever decay with r, okay? So there's some problem here, okay? On the other hand, physical states or states which you can sort of make in a lab maybe, they don't have this kind of a property. So maybe I'll just take 2 minutes and then discuss later on because I see that time is running out. Where is that cloth? The cloth is better. Oh. Oh, sorry. So I should not take this. On the other hand, if you take, for example, this state or that state, these are what I would call physical states. Because if you calculate the same quantity here, then this connected correlation function decays to 0 as a function of r. In fact, if you calculate this thing here, you will straightforwardly see that if you take this thing, then immediately if you move from, you'll easily see that this thing does go to 0. In fact, it immediately becomes 0 as a function of r, okay? Yeah. So these are called short-range correlated states. So these can be prepared in a lab, for example. So now, the thing that happens is, if you have a symmetry breaking, spontaneous symmetry breaking, then if you start from this state, it'll take an exponentially long time. So the time will take an exponentially long time to tunnel to this state. And that's what you call as symmetry breaking. Okay, so if you start from this physical state, it'll take an exponentially long time to tunnel to that other physical state, which is this other thing, okay? And of course, if you are on time scales which are much smaller than that exponentially long tunneling time, you see spontaneous symmetry breaking, right? But the eigenstates for any finite system, they respect all the symmetries of your theory, okay? So that's the simple resolution, that in a lab, you actually start from not these kind of states, but you start from short-range correlated states, and then if you start from this state or that state, it just takes exponentially long to move to its Z2 partner, and therefore you perceive it as a spontaneous symmetry breaking, even though the eigenstates are like that. Okay? So maybe it's a good point to start. I'll stop. I'll continue my discussion of time crystals in my last lecture. Yeah.
Okay, so are there any questions? Okay, if not, then let us thank Arnab. Beautiful talk.